ازاي اسجل هون؟
Thank you, Chair. My name is Wassila Chagra. I'm a lecturer in the Preparatory Institute of Engineering Studies of El Manar at the University of Tunis El Manar. My laboratory is in National Engineering School of Tunis. The laboratory name is Laboratory of Analysis, Conception and Control Systems. The work is entitled Convex Optimization in Nonlinear Predictive Control based on fractional Hammerstein model. I start by presentation the different parts. I will start by presenting the problematic situation. Then I will explain the fractional Hammerstein model. Then I will cite the employed optimization methods. Then I will present the fractional predictive control problem. Then I'll show the simulation results, and I'll finish by conclusion and perspectives. The problematic situation, the Hammerstein, the fractional Hammerstein model is an actual used model in different science areas such as robotic, aerospace, chemical, etc., and many other research topics. Then the nonlinear model predictive control is really a non-convex optimization problem due to the nonlinear part of the model. Then in this work, based on the curve of nonlinear static characteristic of the system, will convert the non-convex problem into a convex one by reducing the search domain and tightening the constraints around the best solution. The major problem caused by the fractional Hammerstein model is that the fractional predictive control algorithm conserves all outputs and inputs measurements. Therefore, it consumes higher calculation time. The main objectives in this work are in using an approach which consumes the least calculation time, which allows less energy consumption and offers good tracking performances. The fractional Hammerstein model is presented by this figure, where it is constituted by two filters, one nonlinear static one followed by a linear dynamic one. The nonlinear function is expressed by this formula, and the linear one is expressed by the fractional Laplace transfer function. Here, the discretization of the model, which is based on the Grunwald-Kletnikov approximation, and here appears all the old measurements of inputs and outputs of the system, which creates the problem of higher calculation time. The employed optimization methods here are two methods, the Nelder-Mead method and the honey badger algorithm. This algorithm is recently developed. It is meta-heuristic. It is based on the positions between the honey badger animal, which is a predator animal. It is based on this matrix, which is composed of the positions of honey badgers from their preys. Then this is the adaptation of the position, and it is the adaptation of the algorithm is based on the smell intensity, the smelling intensity, which increases if the concentration of smelling is higher, and decreases if this concentration is low. So this is the adaptation law of the algorithm, which is based on 6 radii, which are between 0 and 1. This is the flow chart of the algorithm, which is composed of the initialization step, here the exploration phase and the exploitation phase. The other algorithm is the famous Nelder-Mead algorithm, which is stochastic true and based on simplex, which is a polygon with n plus 1 vertices. N here is the problem dimension, which means the number of variables to be estimated. The evaluation of the objective functions is carried on for each vertex, and then the vertices are sorted, and then the worst point is changed by its symmetry, so it is the distance is expanded or contracted, and then the point is replaced by reflection. So the algorithm goes from the initial simplex, it is transformed, deformed, then moved and reduced, and until reaching the minimum of the objective function. Then the presentation of the fractional predictive control problem, which is based on a prediction model that calculates the predictive output, the definition of a cost function, and the employment of an optimization algorithm, which is run at every iteration to determine the control solution which is applied to the system to generate the current output of the system. Here the different variables of the algorithm, and then the objective function, which is the criterion G, is expressed as the sum of two terms. The first term is the squared error between the set point and the predicted output, and the second one is the squared control increment weighted by real weight lambda. As simulation results, we have considered two examples, one with odd degree and the other with pure degree. The first one with odd degree, in which the characteristic is increasing for all control input values. Then the nonlinearity is given, the static nonlinearity is given by this expression, and the linear model is given by this fractional Laplace transfer function. It is then discretized, and this characteristics, this static nonlinear characteristic is obtained representing the curve of the output y versus the control input u. Then in this figure we note that for each set point value corresponds only one control input solution. For this set point value 8, which is equal to 8, there is this value which corresponds to this minimum of the criterion G, and for this value minus 3 corresponds this minimum of the criterion G. So the problem here is convex, and we see also that the nonlinear characteristic changes with the number of truncated measurements, because we cannot consider all the old measurements. It should be better to contract in an order n key. Here, after considering a number of truncated measurements, we see that the characteristic converges to only one curve. The temporal responses given here with the two algorithms, we see we have only one solution. The two algorithms succeed to attain the solution, the unique solution of the control input. But here we can note that the honey badger algorithm proves better tracking, however it presents some oscillations that can be improved later. Comparing the computing times of the two methods, we can note here that the least computing time is offered by the Nelder-Mead algorithm. Then the second example is given by these equations. This is the static nonlinear expression, and this the fractional Laplace transfer function. It is then discretized and give this static nonlinear characteristics, which gives here a parabolic curve, and for each set point value correspond to solutions of the control input. Then the problem here is non-convex, and we see here the convergence of the curve versus the number of truncated measures. We consider at first the non-convex problem with the two solutions. So here we can select between solutions. We can consider this is the best solution because it offers the less energy consumption. Then the temporal response gives these results where the honey badger algorithm sways between the two solutions for the same set point value. However, Nelder-Mead method, it keeps the same solution of input control, but it sways for the other solution when changing the set point value. So here the problem that these oscillations create damage of the actuators and allow more energy consumption. So here, if we will consider only a convex problem, will reduce the research domain and reduce the constraints. After considering the convex problem, we have only one solution. The two algorithms succeed in attaining the best solution, and here we note that the honey badger algorithm proves the best tracking performances. So that in conclusion, we can say that in predictive control of nonlinear systems represented by fractional hammerstein model, the two stochastic methods are used. Honey badger algorithm and Nelder-Mead have been used to resolve the non-convex optimization problems. So the Nelder-Mead offers the advantage of least computing time. However, the honey badger algorithm have a drawback in high variations of the control signal. This is lead to high energy consumption. In considering the convex problem, we reduce the constraints and we tighten the constraints around the best solution. So the honey badger proves an advantage which is better tracking performances. So the perspectives of this work will address employing a hybrid algorithm combining Nelder-Mead and honey badger algorithm. In addition, we'll address an application for of the proposed predictive controller to real processes. Thank you for your attention.